Hello students of science. In this video we're going to talk about radioactive decay, something that a lot of people have heard about but not a lot of people understand. With radioactive decay, that is going to be the spontaneous disintegration or falling apart of a nucleus into slightly lighter nucleus. So here we have uranium, it's going to break down to thorium, break down to radium, to radon, to bismuth, and to lead. Obviously this has been simplified a little bit, but we have a very heavy nucleus, uranium, the heaviest and naturally occurring one, is going to break down into lead, which is a much lighter one by comparison. The key thing to know about radioactive decay, it's always going to lead to a more stable nucleus. It's not going to decay. It's not going to break down to result in something that's going to be more unstable, something that's more likely to break down. It's only going to end up with something that is going to be more stable. When it breaks down, this is going to be accompanied by release of particles, electromagnetic or EM radiation, or both. And there I have the alpha particles, the beta particles, and the gamma rays. So these are particles. This is going to be an electromagnetic radiation there. So stuff is going to be given off when stuff decays. Any atom with an unstable nucleus is called a radioactive nuclide. So remember, nuclide is the nuclear chemistry version of an element, and that's going to undergo radioactive decay. The different ones that we're going to have right here, we're going to start with our alpha particle. That is going to be the symbol right here, or the other symbol that you'll see for alpha particle is going to be total mass of 4, 2 protons, and of course 2 neutrons, and the helium nucleus there. The charge on this is going to be +2 because of those 2 protons there. An alpha particle is essentially 2 protons and 2 neutrons, essentially a helium nucleus. A beta particle, there's our symbol right here, that one is also going to be represented like this with a total mass of 0 and a total charge of -1. This one is going to be our beta particle. Charge of -1. This essentially is an electron emitted from the nucleus. There's no fundamental difference here. We just call it a beta emission because it's an electron that is released from there. We've also got a positron, which is very similar to a beta particle. You'll notice that they use the same symbol here. When I write out the symbol here, it's going to be slightly different because it's going to be a +1. Charge on this +1. And of course, this is going to be identical to an electron. It just happens to have a positive charge. Very, very similar to it. Same mass, opposite charge. And we sometimes write them the same way here, beta emission. But this one specifically is a positive, a positron. And then, of course, we have gamma rays. Here's the symbol for that. And here we would write that out like that. This has a charge of 0 because it's not actually a particle. This is just a high-energy electromagnetic wave. In electron capture, an electron is essentially captured by the nucleus of its own atom. This is important because it's going to change the number of protons on there because it's going to be converting a proton into a neutron. So here I have an electron that's going to be captured by this nucleus, and you'll see it turns this proton into a neutron. So it went from beryllium-7 to lithium-7. So the total number of protons changed, which of course means we are looking at a different element. A proton is changed to a neutron when it captures that. Here I have carbon-11. Note this positive charge right there. That is going to be converted into a neutron, so it stepped down in the periodic table. The number of protons dropped from 6 to 5, and the number of neutrons increased from 5 to 6. So carbon changed into boron, and that charge went away. So there's going to be no change in the atomic mass. So the total mass hasn't really changed, because nothing's really gone away. But we have a change in the atomic number, which means we have a different element. Here I have potassium, so it's potassium-40, that's a total mass there. It's going to change into argon-40. No change in the total mass, but one of those electrons has been captured by the nucleus, and I went from 19 protons to 18 protons. So different element has been created. Half-life kind of relates to this. Half-life is the time needed for half of the amount of a radioactive nucleus to decay. So here we have the decay of carbon-14. So let's say we have 10 grams originally that we're going to be starting with. So we're looking at this on percentage. The half-life of carbon-14 is going to be 5,730 years. So here I have my initial start of 10 grams. 5,730 years later, I'm left with 5 grams. 5,730 more years, I'm left with 2.5 grams. Another 5,730, I'm left with 1.25 grams, and so on and so forth. Each time, half the amount is going to be removed. Each radioactive isotope, whether it's carbon-14 or carbon-12 or whatever it is, has its own unique half-life. Some of them are on the order of seconds, some of them are on the order of billions of years. Let's take an example here, so don't copy this. Let's say we have a radioactive isotope with a half-life of 1 day or 24 hours. Let's say on Monday, T0, that's just time 0, we have 128 grams of this. Well, Monday We start with that. Tuesday, we're going to have half of that, because remember, each day, half of it's going to go away. So I started with 128 grams. The next day, I'm left with 64 grams. Wednesday, T equals 2, I'm going to be left with 32 grams. Again, half of what I started. Thursday, 16 grams, half of what I started. Friday, T equals 4, 8 grams. Saturday, 4 grams. And Sunday, I am all the way down to 2 grams. So with a half-life of 1 day, I went from 128 grams to 2 grams in a week. If you graph this out, you see this half-life equation, where each day half of it is going to be removed. That's how half-life works. Each day, half of it is just going to spontaneously break down and escape. Of course, we can also do artificial transmutation. So that's the creation of a synthetic element. That can be accomplished by hitting the nucleus of an atom with either charged or uncharged particles. Here I have a very heavy element right here being hit with an alpha particle, 2 protons, 2 neutrons. If it's fast moving enough, I'm going to end up with a new element. This is sort of smashed together and it's added some. If you don't hit it with a fast enough alpha particle or something else like that, it's just going to bounce right off. But if you get it fast enough where it smashes in and it can stick there, we have a new element. Anything heavier than element number 92, which is uranium, they're called transuranic elements, and the only way you ever see them in the universe is that they were artificially created. We would say these are man-made or synthetic elements. This isn't even complete. We actually go all the way out here to 118. But everything here, so here's uranium 92, everything after this, completely synthetic, completely made by man.